So let me start. So today I'm going to talk about the contributions of various processes to the intended variations of North Atlantic subtropical water and its derivation in climate models. So first I want to acknowledge my collaborator, Dr. Eddy from the University of Washington. So what I'm going to talk about basically from the summary of the two papers published last year. So the two studies is part of the contribution to climate water dynamics experiment, which is called CLIMODE. So CLIMODE is a dedicated program to quantify the processes that influence North Atlantic subtropical water. The subtropical water in North Atlantic commonly called 18-degree water because of its nearly constant in temperature around 18 degrees C. So throughout my talk, I'm just going to use EDW. So just before I go into my talk, I just want to quickly mention the processes that influence the 18-degree water volume. So the 18-degree water is formed by heat release to the atmosphere during wintertime. Is then subsequently dissipated by mixing and subducted away from the formation region. So first, I'm going to talk about the importance of the EDW for climate, and then show you the observed intended variations in EDW volume. So the third part of my talk is going to be focused on to investigate the contributions of various processes to the observed EDW volume anomaly by using a simple box model. And the last part, I'm going to focusing on the evaluation of climate models to examine the ability of IPCC class models to simulate 18-degree water. So why it's important to study EDW? Let me just start with this well-known figure of heat transport by atmosphere and ocean. It's meridian of heat transport. The black line shows the total and the blue line is the atmosphere and red for the ocean heat transport. So what I want to point out is in the tropics, the gain of northern heat transport by atmosphere mainly comes from the heat loss from the ocean. So therefore, the heat release from the ocean in the tropics can have influence in climate. So let me just using examples of storms to indicate the importance of the Earth's interaction with the tropics. So you see that near the South Stream where you have the large heat loss, which is the location where you have more storms generated. And although the storms are stronger in the tropical gyre region, but the storm intensification actually in the Gulf Stream region. So this indicates the importance of the heat release from the Gulf Stream. So the heat release to the atmosphere is actually in the Gulf Stream region is related to the heat source in the ocean. So this plot shows the anti-correlation of heat content, which we use SSH as a proxy, and the turbulent heat flux. So we get the similar anti-correlation with the use of nice air surface flux. So basically, this the heat flux is in terms of ocean. So if you have a lower value, means large heat release to the atmosphere, you see that if you have more heat content, you have large heat release to the atmosphere and vice versa. So previous work also found that the 18-degree water has a negative correlation with heat stored in the ocean. So if you have more, basically the EDW is specific heat reservoir. If you have more 18-degree water, and indicates you have less ocean heat stored in ocean, and if you have less 18-degree water, you have more heat. So in the ocean. Therefore, it's important to understand processes contribute to the EDW variability. So now I'm going to show you the observed internal variations in EDW volume. So basically, this figure just gives you an idea of EDW distribution. This is the thickness average in January, February, March. There are two criteria used to determine EDW. So the temperature has to be within 17 to 19 degrees C, and the vertical temperature gradient has to be less than 0.06. So you can see that the changes from year to year, not only the spatial distribution of the EDW, also the thickness, both contribute to the variability of EDW volume. So I should mention that so the areas you see that EDW, not all those areas are outcropped. So which means that some areas is not locally formed, it's actually subducted from formation region, which is, you can clearly show if we look at the outcrop of 17 to 19 degrees C. This is a year that the 19 and 17 degrees C outcrop. And on the left is the years we find thick EDW rather than 100 meters. You see that the outcrop is mainly boxed to the northern part, and the southern part is mainly subducted from formation region. So basically, the overlap of the two, the outcrop and the thick EDW, is the formation region, and the southern part without outcrop is subducted region. So here we separated the EDW to the two regions because it's likely to have a different controlling process for the variability in the two regions. So here is the volume of EDW in two regions. The blue line is the EDW in formation region, and the red line is the EDW in the subducted region. So you can see that in the formation region, you see this strong annual cycle due to yearly formation, and in the subducted region, it's mainly controlled by the internal variability. So here is the internal variability, removing the seeding cycle. So, so similar to what was found before, so if we look at the EDW volume and the SSH as a proxy for heat content, we see this anti-correlation between EDW and heat content, indicating in both formation and subducted regions. So indicating that the EDW is deficit of heat reservoir. So, so what controls the EDW variability in two regions? We solve those where we use a simple box model to look at the different processes. So the simple box model, we perform the model in two different regions. In the formation region, the volume change basically comes from formation, and it's lost by transfer to the subducted region and also by mixing. And in the subducted region, the volume change basically controlled by the transfer from formation region and lost by mixing and other processes like advection. So the data used in the model, as I showed before, the 18-degree water volume is determined from World Ocean database. This is a 3-month temperature map. The formation of EDW is computed from LCH Flux and SSH from OA Flux products. And because the mixing and loss of transfer loss terms, we don't have enough data to compute, so we are going to use some Proxies to look at those process. This is mainly based on previous study in other regions. So for the mixing, we're going to use the downstream pathway. So I'm going to show you previous study with its reading was users. And then for the, we'll use surface velocity as proxy for transfer loss, both the Gaussian path and the surface velocity from chemical SSH. So as I mentioned that the formation can be computed directly from LCD flux and temperature. So the formation basically is the difference between water entering and leaving the 18-degree water temperature class. So the water entering a temperature class basically has a transformation indicated on the top, computed from LCD flux and temperature in this area of the temperature of class. So for Proxies, based on a previous study in the subtropical North Pacific from Zhu and Chen, what they found that for the subtropical water in the North Atlantic, the volume is really related to the mixing. With mixing, you can it's indicated by the state of the spatial extension. When spatial is stable, in the past is shorter, and so you have a less mixing and low P rate, and then you have a normal water formed. And during the period when the spatial extension is unstable, you have longer paths. You have high PV, more mixing, and low formation of the molten water. So also what they found is that the subtropical water in the North Pacific is not related to the heat loss. That's kind of surprising. So following their study, so we're going to use the Gaussian path as a proxy for mixing. Here's two examples of the Gaussian path. So the color map is SSH, and the black line shows you the Gaussian path. You can see in March 2003, you have a really long path with more meanders, which indicates more mixing. And in March 96, the Gaussian is stable, and you have a shorter path, less mixing. So a previous study also indicated that the EDW loss is also related to the advection, the water advected opposite the region. So we are going to use velocity to approximate the loss by advection. There are also other studies indicate that the mix layer depth gradient kind of dominates subduction. So we tried using this layer depth difference in two regions to approximate the transfer term between the two regions. So let me just first show you so we studied the model with the simplest model, only including the formation and the constant rate of loss to see how much the volume change is explained by the formation. So here, this is the formation region. The black line is observed EDW volume, and the right curve is impact from the model. So you can see that the formation is reasonably simulate the EDW changes in formation region, and the lower panel here is the internal variation. So this is for a longer period from 1985 to 2007. However, we may use Proxies for mixing and loss terms because we use altimetry, so our study is limited to 1993 to 2007. So I'm not going to talk about all the models we performed. Here I'm just showing you the bias model showing on the top here. So we have formation, and we have this mixing loss proportional to Gaussian pathway, and this transfer term to the subducted region. Subducted region, this loss term, they are proportional to the filter velocity. So the plot here shows you the comparison of two different models. So the right line here for the formation region indicate that we're including the Gaussian path as a proxy for mixing, and the blue line is when we use results, is not including the Gaussian path, just to give you an idea how this improves the model. And so the lower panel here is for the subducted region. The comparisons also again with results including the dystrophic advection terms. So I should mention that in all those loss terms we have the EDW volume to scale the loss term, because we found that the loss of EDW actually proportional to, it's significantly correlated with the volume itself. That's what we include that to scale all the terms. So let me just summarize for all the models. Basically, we say that for the formation region, if we use just to look at the formation, it's saying 30% of the EDW variability. This is our unentangled time scale. And you see that it's for the formation region, with including Gaussian path for mixing, you can see the significant increase of the variance exchange at the model. And in the subducted region, you see the increase by including the dystrophic velocity as a transfer term, and also loss to the other regions. So let me just summarize for this provisional part. So based on the two simple Flux model, well, we found that the formation does explain some of the entangled variations in the EDW volume change. This is different from what was found in the North Pacific, where Chen and Chen did not find a relation between formation and the subtropical water changes. So the model also indicates that the Gaussian path is as a proxy for mixing, also explains part of the EDW volume loss. This is consistent with what was found in the North Pacific. Also, if we include the advection term for loss, this also improves the model for the subducted region. So let me move on to the evaluation of models. So the goal is to examine the ability of having models in simulating 18-degree water process. So there are three models we used. Two models from IPCC AR4, CFD-LCM 2.1, and NCAR-CC-SM 3.0. So those are two widely used models. And I'm not going to talk about the setup. The data we used is for 50 years, from 1950 to 2000. It's monthly output. Another model we use is data simulation model from JFPL. It's coupled data simulation. Basically, it has the same model setup as JFPL 2.1. So the purpose is to look at the data simulation process, whether it improves or derives the model dynamics and thermodynamics. So the data used in this part to compare with models is similar to what we used for the data analysis part. The EDW is computed from World Ocean Database with a 3-month temperature map, and we computed the formation of 18-degree water from OA flux products, and we also used that altimetry to look at the Gaussian system and also the kinetic energy. So before we compute the 18-degree water from models, because models may have a temperature bias, so we need to look at what temperature class of the EDW fall into each model. So on the top left is the volume of water at different temperature class. So you see that from observations and the data simulation model, basically the volume peaks around 18 degrees C. And for the IPCC, the two IPCC IPCC models, you see they have their cold bias. The volume kind of increase toward cold water, but you do see a local peak well within the 19 to 17 degrees C. And on the right is an example of the temperature section around 55 degrees west. This is time mean. So you see that the thick isothermal layers all fall into a 17 to 19 C. So another point we look at is transformation. So from observations and models, you see that the largest transformation is around 19 degrees C, although the models does not capture the strong sequence of transformation between 19 to 18 to 17. So based on this, we use the same criteria as we used for observations to determine 18 degree water volume, as indicated here. So the plot here shows you the spatial distribution of EDW thickness. It's mean, the average for the study period. So what you see that in the observations on top left, the thick EDW basically follows the Gulf Stream very well. The green line is the Gulf Stream, but the observations is determined from altimetry, and for the models is determined from each model based on the maximum velocity. So you see that in the observations, the thick EDW follows the Gulf Stream very well, and this is, you can see that in the data assimilation model, but in the IPCC model, particularly for CM 2.1, it's kind of further to the south, and where for the observations, the thick EDW is within 7 degrees of Gulf Stream. Also, you see that the thickest EDW is located to the east of 60 west. So all models capture this feature. And you also notice that all three models give you thicker EDW compared to what we estimated from observations. However, if you look at the formation, actually the observation gave you the strongest formation rate, where the model is kind of relatively weaker. Also, you see that the formation from observations is also well follows the Gulf Stream, but not in the two IPCC models. The data assimilation model in green brighter. So also I want to mention that for the plumbing models, the formation is kind of restricted to the west, particularly in CM 2.1. So it's really further to the west compared to observations. It's extended. In the observations, the formation has extended to 40 degrees west. But for the CM 2.1, it's kind of to the west of 55 degrees west. So on the figures, the lines are isothermal. You can see that this is also related, and the formation kind of related to the outcrop of the isotherm, which is 2000 west. And the formation is closely related to the air-sea heat flux. So this shows you the wintertime air-sea heat flux is mean from OA flux and the three models. OA flux is on top left. So you see that some observations, the strong air-sea heat flux along the Gulf Stream. And the data assimilation also shows the strong heat flux. The CCSM3 shows a little bit also better than the CM 2.1, which is too weak, and the large heat release is confined to the west. This explains why the formation also constrained to the west in CM 2.1. So the distribution of EDW information is likely related to the representation of the Gulf Stream system in the models. So So on the top left is the bead and in color from altimetry, and the arrows show you the direction. And on the top right is from data simulation model, and below 2 panels from IPCC models. So you see that from observations, the IPCC, from observations, the Gulf Stream is very strong and narrow, but then from models, it's relatively weak and broad. So there are two effects from this efficiency of simulating Gulf Stream system. So first, the Gulf Stream is too weak in the models, so it's unable to transport warm water efficiently enough to the east to precondition for the multiple formation in the eastern region. Also, the wide Gulf Stream in the models kind of transports the water from in the western region to the east, which explains why in the models the formation is constrained to the west, but you do see a thick EDW to the east. So before I show you the inherent variability, so I just want to use this figure to show you the seasonal evolution of EDW volume. On the left, on the right is the seasonal cycle formation rate. So this, so for the seasonal cycles, I use the Argo because the World Ocean database is 3 months averages. So the Argo has monthly data getting me a better temporal resolution. You see from Argo, you see the EDW volume peaks in April, and but in the models they all peak months early, and this is connected to the formation rate. The formation estimated from observation, the blue line, peaks in February, and it's data simulation peaks at the same time, but it's weak. And the two models peak 1 month or 2 months early. This explains why the EDW volume peaks early. So this is related to the bias in the model temperature, which in later months you don't have this outcropping from the water. So also I did not show here, but I want to point out that the seasonal cycle of EDW volume is 80 to 90% is explained by the thickness. It suggests that the vertical erosion plays a dominant role in seasonal diffraction of EDW water. This is true for both observation and model. So this will show you the spatial distribution of inherent variability of EDW thickness in color. And the black line is the EDW thickness. And the right line here is the Gulf Stream position. So what you see here that the variability from observations on the top left also follows the Gulf Stream, and it's also co-located with the thickness distribution, where you have thicker EDW have large variability. So the data simulation model tends to capture this feature, but this is not shown in the two IPCC models, particularly in the same 2.1. In the regions you have thicker EDW, you actually have this low variability. So this may be related to, well, before I do that, so this figure shows the EDW volume variability actually contributes by two parts, the area change and the thickness change. So this will show you the contributions from area indicated by the green line, and the thickness change is the red line. So from observations, you see that both components contribute kind of equally to the EDW volume variability with area change has a slightly larger contribution. This is different from seasonal cycle EDW, which is dominated by thickness and thickness changes. So for the model, the data simulation model show a similar amount of variability in EDW volume, but the thickness contribution is relatively larger. And in the two IPCC models, the EDW variability is really weak, particularly in SAM 2.1, only 1/3 of the variability estimated from observations. And this, so both thickness and area contribute to the weak variability. And so what we think that although both ocean and atmospheric process can contribute to thickness and area, but we think that the formation through air-free feedback has larger contribution to thickness changes by the ocean process through advection redistribute of EDW have a larger control for the area change. So this weak variability in the area so may indicate that the ocean surface is too weak in the model to redistribute the EDW. And as mentioned earlier in the analysis of data, the mixing plays a larger role in EDW variability. And here I'm showing you the Eddy kinetic energy from observations, the blue line, based on altimetry, and from models. So you see that this strong Eddy activity near the Gulf Stream does not show up as all three models, although the data simulation model showed it with some. So this is indicating that mixing process is not really simulated in the model. So as I showed before, even though that the data simulation model does not capture the Eddy kinetic energy, the Eddy activity does show this strong EDW volume variability. This may be just simply due to data simulation process tracking the temperature. So simulating the EDW properties is important, but what is more important is the this air-sea interaction process involving the EDW. So as we found before that the EDW volume is an indicator of ocean heat content. It's actually a deficit heat content. When you have a large volume of 18-degree water, you have a low heat content. So here we look at how models simulate this process. So on the left is the time series from observations on the top, and the second panel is from data simulation model, and the third panel is from SAM 2.1, last panel from CJSM 3.0. The right line is the ocean heat content anomaly, and the black line is 18-degree water volume. So you can see from observations, you see this anti-correlation, and on the right is the like correlation from observation models. The blue line is based on observation. So you see this 3 months delay is anti-correlation. So this delay may be due to data resolution. We only have 3 months temperature. So you see this anti-correlation in the SAM 2.1, but you don't see it from data simulation model and the CCSM 3. I think this is that very much. So here we look at the feedback ocean to the atmosphere that look at the heat content and air-free feedback. We found that before the ocean heat content forces air-free feedback. In middle of the region, if you have more heat in the ocean, you can have a large heat release to the atmosphere. So on the top, left is a time series of ocean sea contents, the red curve. And then the black curve is airspace heat flux. So you see this anti-correlation. And the second panel is from couple data simulation and CCM 2.1, CCM 3.0. So on the right is the anti-correlation, left correlation between ocean sea contents and the airspace heat flux. So from observation, you see this anti-correlation with heat content reading airspace heat flux by a year. And both the XCC models, CM2.1 and CCSM3, the red and the green curve, captures this anti-correlation. However, this data simulation model doesn't see this anti-correlation. So let me just conclude the second part. So what we show from the study that data simulation model gave you a better representation of EDW volume, formation rate, and its spatial distribution. However, the data simulation process degrades the model's thermodynamic response to forcing because it does not capture this observed anti-correlation between heat content and 18-degree water volume. Also, the anti-correlation between heat content and airspace flux. Unlike the observed dominant southward movement of the EDW from the formation region, in the models, the EDW actually moves to the east due to the excessive wide Gulf Stream in the models. So that's it. Thank you.
Can you go back to the time series of the volume and heat content? I had a hard time seeing between the black and the red curves. I couldn't see whether, the assimilating model was doing the worst job with the heat content compared to the observations, or with the 18-degree water volume compared to the observations, or it's just not capturing that negative anomaly. Yeah, maybe it's my eyes, but I have a really hard time seeing which of those two is kind of closer to reality compared to the relation.
So the black is data simulation.
Yeah, on the time series on the left.
Oh, this one.
Yeah, I was wondering which one is the assimilating model doing the better job of getting the 18-degree water volume, or getting the in terms of the fluctuations, or the heat content.
I think the volume maybe.
So basically, what's happening is it's getting that, matching the observations by generating kind of spurious heat fluxes that have nothing to do with what's happening.
Yeah, I think they're probably correcting the temperature. You're just putting the heat into the ocean, not really due to acid injection.
Related to that one, I was kind of struck by how poorly the CDA model was actually getting, reproducing the 18-degree water volume. So I guess the model is...
It's just correcting the temperature. So
you compare the two black curves against the top two, that you wouldn't say that the interannual variability is really, remotely kept. I mean, there's maybe the phase lag in places of other places where it's really different. So I guess that means that even though they're assimilating data, and a couple of models are still not dragging the model on to reality.
Yeah.
Very well.
Well, I guess you do say there's low.
Oh.
What different axis?
Phase lag. Okay, all right. That's okay.
Oh.
Yeah, all right, sorry.
So observation I used from 1980 to 2010, but this data simulation model is from 1973 to 2007. That's the model period.
What are the physics for the anti-correlation between the heat content and 18 water degree volume. And why the anti-correlation?
Well, basically the 18 degree water is in the lower water column is kind of a cold water part.
The heating content is from a surface to where?
To 700 meters. This is 700 meters.
Well, the 18 degree is the further up level, region. And your heating content is from the surface to the 700, right?
Yeah.
Maybe you said it, but in the lower panel, how did you compute the transformation rate, or what does it mean physically with the transformation rate?
What transformation?
Yeah, what is it's inverted? I just don't know how is it calculated?
Which one?
That one. The lower panel.
Transformation. Yeah, it's basically. I have the equation. It's here. So this is the transformation rate.
Okay.
Is it the transformation or the formation, the derivative of the transformation that you're showing in that curve?
I think I used transformation.
Because it looks like a big peak at 18 degree water, which I would think it should be the formation.
Well, the peak
right?
is around 19, actually. So the peak is around 19, right? 20 or 19.
Okay, so it's that big convergence there. Is it?
Yeah, it's a different
formation?
formation,
Oh,
yeah.
Okay, gotcha.
Is it getting better if you increase resolution?
What?
Is it really get better if you increase resolution?
You mean increase the model resolution?
Yeah.
Yeah, I think so, but I haven't looked at the high resolution model.
And people in Japanese is
Yeah.
the model, the high resolution.
Yeah.
Another thought too, when you were showing the different paths for the Gulf Stream and the different models, I was thinking that in addition to the things you mentioned, maybe one of the reasons why the models want to form or have that big formation maximum in the west is because of the overshoot, right, of the boundary current.
Yeah.
They all separate.
You mean
so
this
they
one?
Immediately get into a cold atmosphere right there near the west of the boundary.
Yeah, I think so. This is what I talked about in the paper.
Okay.
This overshoot actually, consumes the formation.
And the reason you argue for that anti-correlation in some of your earlier work is that when there's a lot of heat content, it just doesn't have the time to lose heat to generate 18 degree water, right?
Mm-hmm.
It's too warm.
Yeah.
But in the models, if it's really sluggish, there's more time for it. And yet they said the anti-correlation with the sluggish cold.
Yeah, I think so, because I looked at the decorrelation time scale in the model. If I look at the physical heat content or physical temperature, heat content, it has a really long decorrelation time scale in the model, but the observation kind of shorter. So you kind of have a quick difference.